Hey guys, this is 6.2. We are talking about one-to-one functions and inverse functions, okay? So in 6.1, we were working on compositions of functions using the two functions. The two we used were f and g. And when we compose those last functions, f of g and g of f, in the last example, they turned out to be what we call inverse functions because they each, when we compose them together, quickly simplified to x, right? So the rules of inverse functions will undo each other and you will be left with x in the end, all right? All inverse functions are one-to-one functions. So we're going to start with what is a one-to-one function. Okay, a function is one-to-one if all inputs are unique and all outputs are unique. Inputs are x values or the domain, the values of the domain, right? And all outputs are y values or your range. Yeah. So if all x values are unique and all y values are unique, it is a one-to-one function. Okay. So a function so for an equation to be a function, every input, every x value has to have a unique y value. For a one-to-one function, the x values must be unique and the y values must be unique. Okay, so here are some maps, and we're just going to decide whether each example, here's example 1, here's 2, and here's 3, is each example a one-to-one function. Okay, so you have your domain, your x values are your inputs. Your range is your y, which is kind of obvious because they have x and y. They helped us there. These are your ins, these are your outputs. Okay, so for every single ordered pair in each one-to-one mapping, x is unique and y is unique. Neither will ever repeat. Okay, x sub 1, x sub 2, x sub 3. Each of those are different. No value is used more than once, right? Y sub 1, y sub 2, y sub 3, all those values are unique. So that means that this is a one-to-one function. Okay. Sorry. Same thing, we have our x's, we have our y's, our inputs and our outputs. Each input needs to be unique and each output needs to be unique. So this x sub 1 corresponds to y sub 1. X sub 2 also corresponds to y sub 1. That means we have this point and we also have this point. So y sub 1 is no longer unique. So this would not be a one-to-one function. Here we have x sub 1 corresponding to y sub 1 and x sub 1 corresponding to y sub 2. If you remember, a function for a function, every x can only ever have one y. Yeah, so this is still a function. This x only has one y, this x only has one y. It's okay that they have the same y, but here one input has two different outputs. That can never be a function. So not only is it not a one-to-one function, it is not even a function. Not a function, not a one-to-one function. So weird that I wrote it a different way every time. Need to be more clear. Clarity. All right. Example 1. Determine whether the functions are one-to-one. We have a mapping here and we have a group of ordered pairs. So in this mapping, we have a 35 going to a 55, a 41 to a 35, a 45 to a 33, a 53 to a 35. So our X values are unique. These would be our X values because we are putting them in, right? And we are getting out the HDL or our Y values. So these seem to be unique. That's good. However, over here, these are not unique. 35 is used with, I should write it like 35 is used with 41. 35 is also used with 53. Good. Each value does not have a unique Y value, so it cannot be a one-to-one function. In this set of ordered pairs, we have -3, -2, -1, 0, 2. So nothing is repeating. So the X's are unique. For Y, we have 5, 3, 1, -1, -3. These are also unique. So this would be a 1-to-1 function. This one is not a 1-to-1 function. Okay. The mapping is not one-to-one. The ordered pairs is an example of a one-to-one function. All right. If you have the graph of this, you can use a horizontal line test to determine whether or not the function is one-to-one. So remember that a vertical line test tells us whether an equation is a function. The vertical line test means we just thought of a vertical line going across the graph at random. And if that vertical line, if any vertical line ever touched the graph in more than one spot, 0 spots is okay, but more than one spot, that would not be a function, right? So these are both functions. They both pass the vertical line test. But now to determine, is it a one-to-one function, we can use a horizontal line test. So our line, it's the same concept, but our line is going the opposite direction, okay? So they gave us a horizontal line. Here, we could give ourselves our own horizontal line, or even make the x-intercept our horizontal line, okay? So we have our graph of our function. In this case, it would be this guy. In this case, it would be this guy. This to me looks like the graph of f of x equals x squared, right? It's a parabola. This one looks like f of x is x cubed, okay? And then we just give it a horizontal line. Here we say no, right? This is not one-to-one. This one, you're like, way down there in here, it looks like it goes straight, right? And maybe it does, but if it is x cubed, it does not. So let's look at, that is, yeah, that's okay. All right. If I zoom in on x cubed and get really, really close to 0, you can see that it's changing with each new point. Even though that's a really, really, really small number, that number is changing each time. Sorry, that y value is changing for each x value. It's very hard to see, but it is changing. Defaults in quicker. All right. So if that is in fact x to the third, that function is 1-to-1. If it's not, because we don't know that it is, then you can say no. They didn't tell us. They just asked us to look at it. Okay, so that's 1-to-1. You know it now. Every x has to be unique. Every y has to be unique. Now, every 1-to-1 function has an inverse function. The inverse is the separate and unique function that undoes the rule of f of x. Okay? So remember before, in our previous lesson, we had f of x was 2x minus 5, and we had g of x as x plus 5 over 2, right? And we said we could get f of g of x to equal x, and we showed that we could do that. And we could also get g of f of x to equal x, right? We analyzed the functions. Each function's rules undid each other. If you look at it, multiplication by 2 is undone by division by 2. Subtraction of 5 is undone by addition of 5, right? So the test you can do to determine if two functions are inverse is to input them into each other and see if you can come out with simply the variable, okay? So when we have an inverse function, the symbol f(-1) is used to denote the inverse of f and is found by switching the domain and range. Remember, domain is x, range is y. So essentially what we're doing is if f of x has the point xy, then the inverse of f of x will have the point yx. We switch them, okay? We don't literally call these yx, we just took those numbers and we flipped them, okay? The graph of a 1-to-1 function f and its inverse function, f(-1), are symmetric with respect to the line y equals x. Remember, the line y equals x just says that x and y are the same value. So when x is 1, y will be 1. When x is 2, y will be 2. When x is 3, y will be 3. And it follows that line from -infinity to +infinity. So let's look at this. It is symmetric with respect to the line y equals x. So let's look at this. We have y equals f of x, we have y equals x, and we have y equals the inverse of f of x, okay? So if these are inverses, let's just make some points and see if their points are switched for this equation, or sorry, for this function, okay? So let's say if this is f of x, we'll start with f of x. It looks like this point might be 1, 2, right? 1x, 2y. If this point is 1, 2, we're going to flip them, and this point should be 2, 1. 1, 2, up 1. That fits, right? If this one is, this would have to be -1, 1. That means its corresponding point should be 1, negative 1, which it could be 1, negative 1. All right. And if this one is negative 2, negative 1, right? Then this one would have to be negative 1, negative 2, which are plausible, right? 1, 2 corresponds to 2, 1. Negative 1, 1 corresponds to 1, negative 1. Negative 2, 1 corresponds to, sorry, negative 2, negative 1 corresponds to negative 1, negative 2. They are equal distance. There's an equal distance between 2.1 and 1.2. Sorry, there's an equal distance between 2.1 and xy and 1, 2 and xy. These are equal. These are equal. These are equal distances. Okay? So now that we know all of this, I can go back and say that g of x is f's inverse of x, because when I composed g of x with f of x, they canceled one another and they only leave x. And the value f of x equals x is the line y equals x. So y equals x is the line f of x equals x. So when I put these two together, they meet at f of x equals x. And that's why you're always going to get an x out when you compose two inverse functions. So it says the graph in the figure shows a one-to-one function y equals f of x. We don't know what it is, but we know it's one-to-one. It passes the horizontal line test, and we need to draw the graph of its inverse. Here it's easier to see the points because they give us, this is 3, this is negative 3. So this point is 1, 0, right? This point would be 2, 2. This point would be 1, 2, negative 2, negative 1, right? So we found the 3 points. This is f of x. Oh, and they just say f of x is y. Yeah. And then we're going to find the inverse. So they have for us the function, and they ask us to find and graph the inverse function. That means we need to switch x and y coordinates of each point of the line f of x. So just like in this f of x, we went from 1, 2 to 2, 1. We're now going to go from negative 2, negative 1 to the inverse would be negative 1, negative 2, right? This inverse would be 0, 1. And the inverse of this would be 2, 2. So they might share a point there. So we'll start there. 2, 2. 0, 1. So 0 on the x, 1 on the y. And the last point is negative 1, negative 2. We found each point, well, we found each point on f of x, and then we found their inverse point on the inverse function, the graph of the inverse function. I'm going to put these together. I'm also going to add the line y equals x. So that would be 2, 2 would be on that line. 3, 3 would be on that line. 0, 0 would be on that line. 1, 1 would be on the line. Y equals x. It's probably enough points. All right, so this is the line y equals x. And this was the line, the inverse of x. So we can tell that these are equidistant apart. The line y equals x to 1, 0, and the line y equals x to 0, 1. Those are equal distances apart. Those are the same distance, okay? We switched the x and y coordinates and we found each point of f's inverse of x. It is symmetric with respect to the line of y equals x. What if you do not have the graph? What if all you have is algebra? Then we find the inverse of the function algebraically. So what undoes raising something to the 5th power? So if I had y equals x to the 5th, what would undo raising something to the 5th power? It would be taking the 5th root of that quantity, right? So if I have that and I want to solve for x, I take the 5th root. Right? And the opposite, what undoes taking the 5th root of a number, raising it to the 5th power, right? We know that, but we need to prove it algebraically, okay? So the way we would do that is we would take the composition of two functions, and just like before, if you are left with only the variable, that proves mathematically that they are inverses of one another, right? So y equals x to the 5th. The way I would solve that is I would put it under the 5th root. And then I also have its inverse, x equals y to the 5th. So here I get oops. So those are inverses, right? So finding the inverse of a function algebraically. I know how to prove that two functions are inverses, right? But how do we find the inverse of a function? Good. So verify the following are inverse. We verify by taking the composition of the two functions and seeing what you're left with. If you are left with only an x, or the other variable, or a variable, any letter, it proves mathematically that they are inverses of one another, right? So let's look at g of x and the inverse of g of x, okay? So g of x is x to the 5th, and the composition of g of the inverse of g of x is, instead of x to the 5th, I put in that inverse in place of x. So I get the the 5th root of x raised to the 5th power, right? The 5th root cancels out the power of 5. So what remains is g of the inverse of g of x is x. I have proven, I just did a proof. I have proven that these two are inverse. I could even prove it the other way, right? I could say g, the inverse of g of x of g of x is, so I'll start with the 5th root of, but when I see x, I need to put in g of x. So do you see how they kind of just switched positions? The 5 was out here. Now the 5 is under there. They will still cancel. So the inverse of g of x is same cancellation, still x. Okay. Now we have f of x and the inverse of f of x. So f of x is 4x minus 7. I don't know why I did that. I was looking at the 4. And then f of the inverse of f of x is 4 times, instead of x, we're going to put all of this in, 1/4 times x plus 7 minus 7. Okay. So I can say, I can either distribute through this, the 1/4 through here, or I can say the 1/4 and the 4 cancel each other out because this is being multiplied by 4 and this is being divided by 4, right? Four times 1/4 is 4 times 1/4 is 1. Yeah. 4 times 1/4 is 1. But if you want to see it, it could also be 1/4 x plus 1/4 times 7 would become 7/4, right? Minus 7, all multiplied by 4. And then I'm going to multiply all of that. I'm going to distribute the 4. 4 times 1/4 just becomes 1x. 4 times 7/4 just becomes 7 because those cancel. And then that cancels with that 4. Minus 7. And then plus 7 minus 7 equals x. Okay. Or when you're at that 4 times 1/4 x plus 7 minus 7, you can just immediately say these two cancel. I'm left with x plus 7 minus 7 or x. Either way, we've proven that that is the inverse of that. The inverse of f of x is 1/4 times 4x minus 7 plus 7 is, so we just proved that these two cancel, so we'll cancel those. And I keep going. The 1/4 times 8 negative 7 becomes negative 7/4. The 1/4 times a positive 7 becomes plus 7/4. And this was just an x or a 1x. Minus 7/4 plus 7/4 cancel each other out. We just get x. So no matter which order you put it in, these two cancel out and these two cancel out. I know how to prove two functions are inverse, but how do I find the inverse function of f of x? Here are the steps. Step 1, replace f of x with y if necessary. Why? To find the inverse, we have to switch the x and the y values, right? I can't do this if I have no y values. So f of x and y, they're the same thing. F of x just means it's a function. So I need to put in y so that I can switch them. Step 2 is the most important step, the step that actually does anything. We're going to switch the variables x and y. Number 3, we're going to solve for y, and then we are going to use notation to show we have found the inverse. So we replace y with f (-1 of x) to show that this is the inverse. Find the inverse of f of x equals 3x minus 5. All right, I know what undoes. So x is being multiplied by 3, and it's that 5 is being subtracted from it, right? So the inverse of f of x will have to include division by 3 and adding a 5 somewhere, right? Let's use these 4 steps to determine exactly how it will look, right? So step 1 was replace f of x with y. So instead of f of x, now I have it was f of x equals 3x minus 5. Now I'm going to replace it with y. Y equals 3x minus 5. Done. Step 2 was switch x and y. So instead of y equals 3x minus 5, now I have x equals 3y minus 5. Solve for y. All right. Number 3, I'm just going to start where I've written it. Add 5. Add 5. So now I have x plus 5 equals 3y. Divide by 3. Divide by 3. Y is x plus 5 over 3. And like I said, I have a division by 3, which cancels out multiplication by 3. And I have an addition of 5, which cancels out subtracting 5. Good. Step 4 was change the y back to show that we know it's the inverse. This notation says we know what we did is the inverse of f of x. Okay. And then it asks us to graph f and graph the inverse on the same coordinate axes. All right, so those two are the graphs. All right, we have the graph 3x minus 5. That's f of x. I want to make a table to find some points. So I have x, I have f of x, and then I have my coordinates. So for 3x minus 5, if x is -2, -1, 0, 1, and 2, right? Let's just put those in to the equation, 3x minus 5, and see what comes out. So -2 times 3 minus 5. -11. -8. -5. -2. Oops, sorry, that would be 1, -2. Good. So here are some points for f of x. So I can graph that. When x is -2, it's going to be -11, way down there. When it's -1, it'll be -8. It's also off my page. All right, when it's 0, it's going to be -5. 1, 2, 3, 4, 5. There we go, we got 1. When it's 1, it's going to be -2. When it's 2, it's going to be 1. All right, so here's my graph of f equals 3x plus minus 5. And then down here, I will graph f -1 of x. All right, so if I know, ooh, I can do some inverses, right? I know 2 and 1, so maybe my x should be 1. I know 1 and -2, so maybe my x should be -2. I know 0 and -5, so maybe my x should be -5. Good? So if I put 1 into x plus 5 divided by 3, I get 2. If I put -2, oops, sorry. -2 plus 5 equals, divided by 3, I get 1. And if I put -5 in, I get 0. So now I can graph these points. 1, 2, -2, 1, -5, 0. So here's my graph. Of the inverse of f of x. Good. And we need xy to show that is symmetrical according to that. So we graphed it on the same coordinate axis, and we found each equation. All right, so that is one-to-one functions and inverse functions. Thank you so much, and see you next time.